If I write down a U with a 235 and a 92 here, U, by the way, is uranium. Tell me what the significance of those numbers are. What's the significance of the 92 for this uranium-235 nucleus? Megan, you look like you're ready to give me something. Yeah, it's the number of protons. We call it the atomic number. It's the number of protons. What's the significance of the 235? It's not the atomic mass, it's the mass number. The atomic mass is actually an average, right? And that's the number that you see on your periodic table that's that decimal number on your periodic table. That's not the number we actually want. Okay, this is the mass of a particular isotope, which corresponds to the number of protons and neutrons of that isotope. It's always going to be a whole number. Now, if we have 92 protons, how many neutrons are we going to have in this? Nope. 92 protons, how many neutrons are we going to have? 46. How about 143? 235 minus 92 gives me 143 neutrons. Now, I can have another isotope of uranium. Let's make it 238. How many protons is uranium going to have here? The uranium always has 92 protons. The number of neutrons can change with each isotope, and it will, but the number of protons won't. If the number of protons changes, it isn't uranium. It's something else. Now, that can happen, and we'll deal with that today, but it's not uranium anymore if it happens. All right? So how many protons would we have for this uranium? 92. How many neutrons would we have? How many neutrons? Well, 238 minus 92 is 146 neutrons. So this is, as we're covering this isotope notation here, I'll remember that this is not a big topic on its own. This is just more of a tool to help us as we go forward the next couple of days with radioactivity. Okay, you got to remember this, but you're probably not going to get a question on a test that's just this. Okay, it's probably going to be part of a bigger question. Now, let's start talking specifically about radioactivity. We talked about this a little bit yesterday. We defined radioactivity as a natural process, a random process in which a nucleus decays into something else. In other words, uranium-235 becomes maybe thorium-235 or whatever the case may be. It decays into a new nucleus. Why does that happen? Well, we'll go through a couple of different reasons why that can happen in just a couple minutes. But understand right now that it is a natural process, so it happens on its own. And it is a random process. In other words, it happens when it wants to happen. It's like it's got a mind of its own. Now, I gave you an analogy yesterday with flipping coins. If I flip 1,000 coins, how many are going to end up heads? 50%. About 50%, right? On average, 500. Now, if I had to make a bet on it, I would bet that number would be pretty close to 500. It might be 498 and 502, or 503 and 497 or something like that, but it's going to be pretty close to 50-50. We can make predictions about a group of coin flips based on probabilities, but we can't make a very good prediction as to what's going to happen to an individual coin flipping, right? We flip that coin, what's it going to be? Heads or tails? Well, there's about a 50% chance, there's an exactly 50% chance of it being heads and a 50% chance of it being tails, right? In other words, we don't know what's going to happen to it. Why? Because it's a random process. Radioactive nuclei decaying are random processes as well. You look at this nucleus, it's radioactive. Is it going to decay in the next 5 seconds? Don't know. Don't know. But if we look at a big group of them, if we look at 20 kilograms of those nuclei, then we can make predictions about the group based on probabilities, just like we can make predictions about 1,000 coins based on probabilities. But about the individual, we don't know. Right? We don't know. Okay, we can make a 50-50 guess on what's going to happen to it in the next little while. One nucleus decays into something else in a natural fashion, in a random fashion. And the resulting radiation, what comes about as a result of this, what gets released from this process of one nucleus decaying into something else, is called ionizing radiation. And that means that it's radiation, it's these particles that can cause atoms, other atoms, to become ions. And sometimes that's okay, sometimes it's a problem. If we have atoms randomly turning into ions, then chemical reactions can start taking place that aren't supposed to take place, and that can lead to all kinds of things health-wise, including cancers and death, ultimately, because of these reactions that aren't supposed to be taking place. It's really all biology is, right? Chemical reactions. If it's good reactions, the intended reactions, it's all good. If it's bad reactions, the unintended reactions, which can come about as a result of these ions that come from these ionizing radiations, then it's bad. All right, today we're going to spend most of our time talking about 3 different types of radioactivity, 2 of which we've actually talked a little bit about already, not in any kind of major way, but you've heard of, and in fact, you've used alpha particles before. Remember, even way back in Unit 1, we were talking about momentum and collisions. We had alpha particles colliding with other things. We didn't really know what an alpha particle was. Well, today you're going to learn what an alpha particle is, part of this radioactivity thing. We've also learned about gamma rays, gamma radiation. Gamma radiation that comes as a result of nuclear decay or radioactive decay. Energy that comes as a result of nuclear decay. Okay, we're going to learn some more about that today. The only one you haven't heard of right now is beta decay, and we'll make sure that we clarify that for you as well. All right, let me start off by telling you how alpha rays or alpha particles are produced, how alpha decay occurs. Let me define for you 2 forces that act in the nucleus. There are actually 3, okay, but we're going to define 2. There is the electrostatic force, the electric force. The electric force, acts between protons and protons. Positive repels positive, right? It'll also act between protons and electrons, although there's no electrons in the nucleus, so that's not relevant to our discussion here. It will not act between protons and neutrons. Positive will attract neutral, but only if the neutral is a neutral object, so that you can get a separation of charge, if you remember that. So in the nucleus, the electrostatic force is always a repulsive force because it acts between protons. Keep in mind, in other contexts, it can be an attractive force, but in the nucleus, it's repulsive. It's the pain in the butt force that's trying to break up a nucleus. It's the guy that's getting in between this couple that's madly in love. It's trying to push them apart, okay, repel them apart, push them away. Okay, that's the electrostatic force, the repulsive force. Now, there's also another force that we call the strong nuclear force. The strong nuclear force is a force that acts inside the nucleus between proton and neutron, between proton and proton, and between neutron and neutron. In other words, everything inside the nucleus is affected by the strong nuclear force. And that's an attractive force. That's the force that's trying to keep the nucleus together. There is another force, but it's not relevant to what we're talking about here right now. So there is a force that's pushing everything apart. There's a force that's keeping everything or trying to keep everything together. Sometimes a nucleus is too big. Sometimes you got a really, really big nucleus with too many protons. If you have too many protons, that creates an issue. The issue is that the repulsive force is now too big. What's going to happen to a nucleus if the repulsive force is bigger than the attractive force? The electrostatic force is bigger than the strong nuclear force. The nucleus breaks apart. It's like an explosion, right? The nucleus breaks apart. So the nucleus becomes something else. Uranium-235 that had 92 protons and 143 neutrons isn't uranium-235 anymore. Something's broken off because it wasn't stable, because it was that pain in the butt repulsive force that was stronger than the good force trying to keep it together, than the attractive force, the strong nuclear force. Now, the result of this big nucleus with too many protons giving us too big of a repulsive force is that an alpha particle will be released. An alpha particle is just a little chunk of matter that has two protons and two neutrons. Has a mass number of 4, atomic number of 2. 2 protons, 2 neutrons. It's kind of like the nucleus says, you know what, this is hard to stay together. This is hard to stay together. Let's sacrifice a little chunk here. Let's get rid of this little chunk, and maybe we can become a little bit more stable now. Now, it may be stable after that, and it may still not be stable, but it's a little bit closer to being stable nonetheless. Jesse, question? Okay. Now, another name for an alpha particle, 42He, exactly the same thing. Sometimes you'll see it written 42 alpha, sometimes you'll see it written 42He. What's the He stand for? Helium. An alpha particle is identical to a helium nucleus. It's exactly the same thing as a helium nucleus. Somebody in the last class said, does that mean that I can breathe in helium nuclei, alpha particles, from a balloon and talk funny? Perhaps, but that may come as a result of throat cancer from breathing in helium nuclei. Okay, you're breathing in the result of radioactivity. This is ionizing radiation. Okay, it does all kinds of bad things, including causes cancer. It's not the same thing as breathing in helium from a balloon. Helium from a balloon are helium atoms. They're not helium nuclei, they're helium atoms. There's a big difference. Helium atoms are neutral. They're not ionizing. Now, that can create issues in itself. You breathe in too much helium from balloons, and you can literally suffocate yourself because you fill your lungs up with helium and there's no room for air. But it's not a radioactivity issue, and it's not an ionizing radiation issue. If you breathe in these alpha particles, okay, that's a whole other can of worms that you're opening up, even though it's the same thing minus the electrons. Alpha decay, big nuclei, too many protons, the repulsive force wins out over the attractive force. Alpha particle breaks off or helium nucleus breaks off. Now, beta decay, we're going to talk about two types of beta decay. One's called beta minus or beta negative decay. The chunk of the nucleus that breaks off in beta decay is a 0 minus 1 beta. What's that? 42 alpha was helium nucleus. 0 minus 1 beta is, what is that? 0 is the top number. How many protons and neutrons? 0. How many protons? Minus 1. It's an electron. It's exactly what it is. A beta particle is an electron. It's exactly the same thing as an orbital electron, except it's not orbiting. It's an electron that comes out of the nucleus, which, if you're thinking about this right now as opposed to just listening, but if you're actually engaged in thinking, it doesn't make sense. You got an electron leaving the nucleus, and there aren't even any electrons in the nucleus. We'll figure out exactly how that happens in just a moment here, okay? The other type of beta decay is beta plus. 0 plus 1 beta. What's that the same as? Well, 0 means no protons and neutrons. Okay, what's plus 1 mean? 1 proton? Well, no, we had no protons and neutrons. How do we have 1 proton if we have no protons and neutrons? We don't. That's not a proton. That's the antiparticle of an electron. It's antimatter. You ever heard of antimatter?
Yeah. I think Big Bang Theory.
You ever read the book Angels and Demons? Sorry. Have you ever watched the movie Angels and Demons? Oh, there we go. Talk about antimatter and matter, and that when matter comes together with antimatter, it annihilates and becomes pure energy. Yeah, there's some bad science in that movie and book, but there's some good science in it too. Antimatter is, we don't see antimatter often because it when it comes together with matter, it annihilates. But it becomes energy, so you don't see it because it's gone. Um, but it is the same thing as its matter equivalent, except for one property, which is usually charge. A positron, that's what this is a positron, is exactly the same thing as an electron, except the charge is positive. It is not a proton. Its mass is way less. It's exactly the same thing as an electron, except it's positive. Now, let's talk about beta negative for a second. Now, beta negative decay occurs not because we have too many protons making the forces not work out, but we have too many neutrons. Now, it's not a force thing. It's not a force thing at all. It's an energy thing. The result of this is that the nucleus is energetically unstable. It doesn't like having too many neutrons. It's energetically unstable. So what do? We get too many neutrons. What do we do? Well, let me give you an analogy here, okay? In this club, or sorry, in this school, we start a new club every Tuesday. Every Tuesday at lunchtime, we have a club called the Nucleus Club. We don't let everybody in the Nucleus Club. Who are we going to let in this little club of ours called the Nucleus Club? People that are positive people, and people that are neutral, because we want numbers. We're not going to let negative people in here at all, though, right? In other words, we're going to let protons in this club. We're going to let neutrons in this club. Electrons, no way. We don't want negative people in there at all. No electrons allowed. Got it? So a couple Tuesdays ago, we start this club. Everything's good. We got these protons. We got these neutrons. Everyone's happy. Everything's stable. We're all going good. And that goes for a couple weeks. And then last Tuesday, things are starting to become a little bit tense. Yeah. Tense is a good word for it. Yeah. We're becoming unstable, a little energetically unstable. Why? Because a bunch of the protons are going to get together and say, look, like, we like our numbers, but we got a few too many neutrons here. We got a few too many neutrons. And then one of the protons says, well, I got an idea. Why don't we just kick out a couple of the neutrons? Kick out a neutron. We don't like neutrons, so kick them out. Then we got less neutrons. But the other guy says, no, we like our numbers. We like having the numbers. We just don't like the neutrons so much. And then another guy says, well, I got a better idea. Let's take a neutron and change it to a proton. Let's just change a neutron into a proton. The other guy says, no, we can't do that because that violates the law of conservation of charge. You can't take something that's neutral and make it positive. It just doesn't work. It violates a fundamental law. The other guy says, well, what if we change it to a proton and an electron? The other guy says, wait a second, that might work. Neutral becomes neutral. Let's keep the neutron. So we're just swapping a neutron for a proton. One less neutron, one more proton. And what are we going to do with the electron? Because we sure don't like those in the nucleus. Well, let's just get rid of it. Let's kick it out. Gone. That's the beta particle. The neutron is gone now, right? The neutron is changed into a proton. So if you had 10 protons and 10 neutrons here, and the protons got together and said, like, we get too many neutrons. Let's get rid of one. Well, you can't get rid of one because then it becomes 10 protons and 9 neutrons, and we liked our numbers. So what we do is say, let's change one of those neutrons. We had 10. Let's change one so it becomes 9 into a proton and an electron. So now we got 11 protons, right? Still the same number here, but we got an extra proton now. And the electron just has to leave because we don't like negative people in this club.
Okay, so there's too many neutrons.
Yeah.
So they turn
Yeah, that's exactly it. Yeah. We're not there yet. This is the beta negative. Beta negative. Still green right now. Now, positron emission or beta plus decay occurs when we have, once again, too many neutrons. Sorry, too many protons. But all kinds of things can happen as a result of too many protons. Maybe the forces don't work. Maybe the repulsive force is too big. Maybe it's not a force issue at all when you have too many protons. Maybe it's the fact that the nucleus is once again energetically unstable. So once again, we got our nucleus cup. We got protons and we got neutrons in the nucleus cup. But now we got too many of these protons. So they get together and say, well, what are we going to do? Just get rid of a proton? No, we can't do that. We got to keep the same number. I don't know. Maybe we lose our funding if we lose numbers or something. I don't know. Well, we can't get rid of a proton, but what we could do is change a proton. Oh, now we got 10 protons because we changed one into a neutron. Still have 20. Now we have one less proton, one more neutron. So a proton becomes a neutron. Oh, wait, that violates the law of conservation of charge. Positive becomes neutral. That can't work. What else comes out of this? What else comes out of this? A positron. Now it's a positron so that the law of conservation of charge isn't violated. Positron is kicked out. So you've still got a nucleus. It's just a different nucleus. With alpha decay, you got a big nucleus. It's now a little smaller because you've lost an alpha particle. It has 2 less protons than it had before, but it's still a nucleus. With beta negative decay, you've actually got a situation where you have 1 more proton. Maybe carbon 14 with 6 protons becomes nitrogen 14 carbon 14 with 8 neutrons becomes nitrogen 14 would end up being 7 neutrons and 7 protons. And when you have beta plus decay, again, you got something different. It's 1 less proton now. 1 proton gets converted to a neutron. So an extra neutron and 1 less proton. And then this positron gets kicked out. Finally, gamma decay. How many protons in a gamma ray? How many neutrons in a gamma ray? Nothing. What is gamma? What is gamma radiation? It's electromagnetic radiation. It's electromagnetic radiation produced as a result of some other process. Such as alpha decay or beta decay. The nucleus is left in an excited state. The nucleus is excited and releases a gamma ray photon to go back to normal. So it doesn't want to be excited. It's kind of the Eeyore nucleus. Something's happened. It's made it excited, but it doesn't want to be excited. So it goes back down to its normal energy state. To do that, it has to give off a photon. Okay, it's Eeyore. It doesn't want to be excited. So it gives off a photon to go back to being normal. Beta decay has just happened. Okay, beta decay has just happened. The nucleus is left in an excited state. Okay? Okay, picture this. Okay, you're the nucleus. You've just watched a neutron change into a proton and an electron. That's exciting. You'd be excited. The nucleus is excited, but it doesn't want to be excited. So it gives off a gamma ray photon to go back to its normal state. Now, giving off a gamma ray photon doesn't change the nucleus. The other kinds do. Okay, first two, alpha and beta, it's a different kind of radiation. These are particles, right? Gamma is EMR. Alpha and beta change the nucleus. Gamma doesn't, because there's no protons and neutrons. It's just energy. It's the excess energy of the nucleus given off. All right. Now, I'm going to create a couple more columns here. A couple more columns here on the right-hand side, and talk about just a couple properties of alpha, beta, and gamma decay. Those headings are going to be the ability to penetrate matter, or the penetrating power. In other words, you go to the dentist, and the dentist puts that vest on you. Okay, why do they put that vest on you? Because of the penetrating ability of X-rays. We're not talking about X-rays here right now, but something similar. X-rays can penetrate your body, go right through your body, and they can cause damage to your body. So they shield you at the dentist office from X-rays. How much ability do all three of these things, alpha, beta, and gamma, have to penetrate matter? How much ability do they have to go through your body or something else? And the last column is the ionizing potential. The ability to ionize matter. How easily do they change atoms into ions? How easily do they change neutral things into charged things? And then cause those chemical reactions that we don't like happening. Well, here's the good news. Alpha particles have this very, very low ability to penetrate matter. Very low. In fact, usually 3 or 4 sheets of paper will shield something from alpha particles. So you get angry one day and you say, watch this. I'm gonna play a little joke on Mr. Dickie. I'm gonna take out the alpha particle gun. I'm gonna fire those alpha particles right at him and scare him a little bit. Mr. Dickie says, I got the last laugh. I'm just gonna hold up my paper shield and shield myself from your alpha particle gun. Take that. All I have to have is 4 or 5 sheets of paper and I'm just fine, because the alpha particles don't penetrate matter very much at all.
So it wouldn't even penetrate your skin.
No, it wouldn't go through. No, it might penetrate a layer or something, but it certainly wouldn't enter your body. No. Now, I mean, don't get me wrong. It's not to suggest that exposure to alpha particles isn't serious, but it tends not to be so much the exposure to alpha particles out there. It tends to be the consumption of radioactive material that produces alpha particles. So you drink water that's contaminated with radioactive material and it decays in your body, as opposed to the alpha particles entering your body from the outside. Does that make sense?
So if you were to have a bigger greater amount of particles,
Yep.
could it penetrate?
No, it doesn't matter how many you have.
It's like
What do you mean? Yeah, like the photons. Yeah, like the photoelectric effect. Yeah, it is like that. Now, that doesn't mean that it can't do something. Like being exposed to alpha particles can burn you. It could burn your skin, right? But it's not going to penetrate matter to go to your internal organs because it's. I'm sorry? Yeah, it can be. Yeah. They could. Yeah. I don't know. Probably alpha actually, because of the low penetrating power, and then you're going to see something, the ionizing potential in just a moment, and you'll see maybe why that's the case. Okay, let's go to beta. We'll combine beta positive and beta minus actually, because they have the same properties here. Beta positive, beta minus, They're somewhere in between. The penetrating power of beta particles, whether it's beta plus or beta minus, electrons or positrons, is somewhere in the middle. They might be able to penetrate a couple centimeters of flesh, a couple centimeters of your body, but they can't anywhere close to go right through your body. Like a couple centimeters is this. Like they're not going through your body. But the penetrating power is certainly more than it is for alpha particles. Now, for gamma rays, on the other hand, the penetrating power is very high. Several centimeters of lead are required to stop gamma rays. Several centimeters of lead or concrete or something dense and heavy are required to stop gamma rays. They could easily go right through your body. X-rays can go through your body, and gamma rays are more energetic than X-rays. So we're ranking these in terms of penetrating power: alpha, beta, gamma, low, medium, high. Now let's rank them in terms of the ability to ionize matter. In other words, in terms of the damage that they can do if the correct exposure, given the correct exposure here. Alpha particles have the highest ionizing potential. It's very high. So they don't penetrate matter very well, but they ionize matter very effectively. Let's go down to gamma rays. Gamma rays have a really, really high penetrating power, but their ionizing potential is, I don't want to say low, but it's the lowest of the three. And then beta particles, the fence sitters. The fence sitters, they can't even decide whether they're going to be beta plus or beta minus. The fence sitters, yeah, they're the medium, somewhere in between. So,
all around.
yeah. So what's worse for you? Depends on context, right? It really does depend upon context. If you have consumed a material that produces alpha particles, that's bad news. Okay, if I was exposed to something from the outside, I'd probably rather it be alpha particles. From the inside, probably not. Probably gamma or beta. All right.